Welcome to this lecture of number theory. In this lecture, we will quickly review the basics of number theory only. We will not go into the details of the proofs, but we will try to cover up as quickly as possible. This lecture is basically recommended for only those students who have already completed PG in mathematics. So we will just need a quick review and no deep details or the proofs. We will quickly start from the division algorithm. So let's add up division algorithm here. So let's begin here with division algorithm. So what does the division algorithm tell us? If we have two integers a and b, so they are integers in the set of integers with and b is not equal to 0. So we will choose this b as a divisor. Then there exist unique integers. Q and r such that a is equal to bq plus r, where we have the condition 0 is less than or equal to r is less than modulus of b. So what does first of all this division algorithm tell us? We will be given any two integers a and b, but divisor b should be non-zero, with which we have to divide a. Then we can always find a unique quotient which we denote by q and a unique remainder which we denote by r, such that a is equal to bq plus r. But then this remainder has a condition that this remainder is always greater or equal to 0 and always less than modulus of b. So b can be negative here, b can be positive here. If b is positive, then it is just b, otherwise we have to write mod b. So that's our division algorithm. Now let's quickly review the fundamental theorem of arithmetic. So this is fundamental theorem of arithmetic. Now fundamental theorem of arithmetic is stated in this way: if n belongs to the set of natural numbers, then n has a unique representation of the form n is equal to p1 power alpha 1, p2 power alpha 2, so on, pk power alpha k, where pi's are prime numbers and alpha I is greater than or equal to 0, or in fact we don't need to write greater or equal to 0, we can just write alpha I is greater than 0. 1 less or equal to I less or equal to k. So actually we can express every positive integer as a product of prime powers, and in fact in a unique way, except possibly for the distribution of these prime numbers. The prime numbers can be arranged in different ways, but the list of prime numbers will be the same. So this is our fundamental theorem of arithmetic. Now using this fundamental theorem of arithmetic, we will try to formulate the formulas for computing the GCD and the LCM of any list of integers. So let's define the LCM and GCD, greatest common divisor, or this is also known as highest common factor. And these are shortly denoted by GCD, or highest common factor is denoted by HCF. And highest common factor or GCD, they are one and the same things. Now, as the name GCD and HCF suggests, they must be the greatest of all the common divisors between a pair of integers. So how do we define? So given integers a comma b belonging to z, not both 0, then GCD of a comma b, which is shortly denoted as a comma b in the brackets, suppose this is equal to d, then GCD of a comma b is equal to d if we have two conditions on d. The first condition is if d divides a and d divides b. That means d must be a common divisor of both a and b. Now in order to have this d as the largest common divisor, we need this condition: if there is a common divisor c divides a and c divides b, then this c must also divide d. So therefore the first condition is just that d divides a, d divides b, means d is a common divisor of a and b. Now if we have another common divisor c, which is a divisor of both a and b, then c must also divide d. C divides d means c is not bigger than d. So that means combining these two conditions, we just say that d is a common divisor which is the greatest of all the common divisors of a and b. But here we have a nice condition: both of them should not be 0. So therefore if one of them is 0, it's okay, but both of them cannot be 0. So for example, anyway, we will take the example later on, but first we will define the LCM, which we call least common multiple. So accordingly, this is defined as given integers a and b such that a is not equal to 0 and b is not equal to 0. So therefore we have an extra condition than the GCD. If for GCD we need at least one of a or b to be non-zero. but for LCM we need both A and B to be non-zero. Then LCM of A and B is, this is denoted in this way, A comma B in these long brackets. Suppose this LCM is equal to L, then LCM of AB is equal to L if, again we have the two conditions, if A divides L and B divides L. So therefore A must be a divisor of both, A and B both must divide L, so that means L is a multiple of both A and B. And second condition is if A divides some another integer k and B also divides k, then L also divides. So we have the condition is for the least common multiple. L must be the common multiple of both A and B, but if there is another common multiple k of both A and B, then in order to have this L to be the least common multiple, we must have this L also divides k, so that L is the least common multiple among all the multiples of A and B. So again we have the condition A is non-zero and B is non-zero. Now let's try to formulate how do we calculate this GCD and LCM. So calculation of GCD and LCM. So we have the formulas like this given, integers A and B, such that now as we know that every integer has a canonical representation using the fundamental theorem of arithmetic, given integers A and B such that A is equal to P1 power alpha 1, P2 power alpha 2, so on, Pk power alpha k, and B is equal to, suppose canonical representation Q1 power beta 1, Q2 power beta 2, Qs power beta s. Suppose these are the canonical representations of A and B. Then this GCD of A comma B, this is equal to, now as we know that GCD is the greatest common divisor, so what do? Here we pick up the common divisors. We first pick up the common prime numbers from these Pi's and Qi's. So suppose that the common primers are like R1, R2, so on, suppose RL. These are the common list of prime numbers that appear both in A and as well as in B. Now these Ri's may be some Pi's and there are some Qi's, but they are both available in the factorization of A as well as in the factorization of B. Now as Ri is R1 is available in both A and B, so R1 can be some Pi or it can be some Qj. So therefore this R1 will have some power alpha I or it will have some power beta j. Now among those alpha and beta j, we have to pick up the smaller one. So let's call that smaller one as gamma 1. Now suppose we have another common prime factor of A and B, that's R2. So R2 will appear in Pi's and it will also appear in these Qj's, and it will also have some power alpha I here and some power beta j in the factorization of B. Now we will choose the smaller of Pi and Qj. So let's call that smaller as R2. And similarly RL is common between A and B. It will have some power alpha I or beta j. Now let's call the smaller as gamma L. And then this product R1 power gamma 1, R2 power gamma 2 into RL power gamma L, this product will be the GCD of A and B. And similarly the LCM of A and B. Now what we have to do for the LCM, we will pick up all the prime factors of A and B. So let's call the list of prime factors of A and B as, suppose this is the full list of prime factors, R1, R2, so on, RT. Now some prime factors may be repeated, but we don't have to repeat them here. We will list all the prime factors of A and B. Now as R1 is available in either A or B here, then it will have some power alpha I or beta j, but we will have to pick up the bigger power here. So now here let's call that bigger power as let's call the bigger power as delta 1. So R1 will appear either in A or in B. If it appears only in either A or B, if it appears in only one of the integers, then we just have to pick up the power of R1. But if it appears in both A and B, then we have to pick up the largest power of R1. So similarly for R2, suppose the largest power is delta 2, and for RT the largest power is delta t. Then this product will be the LCM of A and B. So now here we will try to have one example. So let A is equal to, let's take the numbers as a prime that are already prime factored. So 2 power 3, suppose 5 power 4, and 7 power, anyway, let's call it 7 power 1. And let's take another integer B as, suppose 2 power 2, 3 power 1, and suppose 5 power 2. Now let's find the LCM and GCD of these two numbers. Then GCD of this A comma B. For GCD we have to pick up the common prime factors first. So now common prime factor is 2 that appears both in A and B, and similarly 5 that appears both in A and B. Now in A, this 2 has the power 3, in B 2 has the power 2, so we have to pick up some other power, that is 2. Now for 5 has power 4 here and 5 has power 2 in B, so we have to pick up some other power. So this product, that is 4 into 25, that is equal to 100. This is the GCD of A and B. Now second, LCM of A and B, we have to write all the prime factors. So the prime factors are 2 that appears both in A and B. Now another prime factor is 3 that appears only in B. Now another factor is 5 that appears both in A and B, and another prime factor is 7 that appears in only A. Now among these prime factors, since 2 is available in both A and B, we have to pick the larger power of 2, that is 3. Now next to 3, it appears only in B, so we have to pick its power, that is 1. Now 5, it is available in both A and B, we have to pick the larger power, that is 4. And 7 is available only in A, so we have to pick its power, that is 1. So whatever is this product, that is the LCM now. Okay, now let's take up some more properties of LCM and GCD. So we have some properties of GCD and LCM. So let's list the first property as this GCD of A comma B into LCM of A comma B. This product is always equal to modulus of AB. Why do we take modulus of AB? Because GCD is positive, LCM is also positive. So therefore this product has to be positive. Second, we can take this GCD of A comma B. This is equal to GCD of minus A comma B. This also equal to GCD of A comma minus B. This is equal to GCD of minus A comma minus B. Third one, GCD of 0 comma suppose A, while A is not equal to 0. This is always equal to A, not actually it is modulus of A. Because if A is negative, then plus A has to be the GCD. And similarly, the fourth one, the LCM has the property LCM of A comma B. This also equal to LCM of minus A comma B. This is equal to LCM of A comma minus B. And this is equal to LCM of minus A comma minus B, provided both A and B are non-zero. For LCM, we need both A and B to be non-zero. Now, if we have to find the GCD and LCM of more than two numbers, like we have the GCD of A, B, C, we can take it in this way. We can first find the GCD of A comma B, then find its GCD with C. Suppose GCD of A comma B is equal to D, then C. So this will be the GCD of A, B, C. And we can have the similar formula for LCM also. So we can have like LCM of A, B, C. This can be defined as LCM of A comma B, then C. So this is LCM of A, B comma C. So now if LCM of A comma B, it's equal to suppose L, then L comma C. This will be the LCM of A, B, C. And we can extend the same formula to the more number of integers given. So suppose if we have the list of 4 integers like A1, B1, C1, A1, A2, A3 and A4, then we can first calculate the GCD of A1, A2, then A2, A3, A3, A4. Then we can calculate the GCD of those GCDs, and that will give us the GCD of 4 numbers or a higher list. Now we have now some very nice property, and now let's take up another property of these numbers. GCD of MA comma MB. This is equal to M times GCD of A comma B. And similar formula for LCM is MA comma MB. And the LCM is equal to M times LCM of A comma B. And let's also mention of this formula, this GCD of ABC and LCM of ABC. This is equal to product of ABC with modulus. Now as we know, LCM is defined only for A and B, C must be non-zero, and GCD is defined provided at least one of A, B and C is non-zero. Now let's take up one nice property of this GCD and LCM. So that is the Bezout's identity. Bezout's identity states that if D is equal to GCD of A comma B, then there exist integers x and y such that D is equal to AX plus BY. So therefore, whenever D is the GCD of A and B, then we can always find integers x and y such that D is equal to AX plus BY. And in fact, the number of solutions of this equation is infinite. We can find infinitely many pairs of A and B such that D is equal to AX plus BY. We can also generalize it. Generalized version is like this. Generalized version of Bezout's identity if D is the GCD of A1, A2, AK, then there exist integers say x1, x2, so on, xk, such that this D is equal to a1x1 plus a2x2 plus so on plus akxk. So therefore this is the generalized version of Bezout's identity. Okay, now let's move forward to have some more results regarding the GCD. So this is a kind of a theorem, or we just need to remember these nice properties. If, let's call this 1, if GCD of A comma B is equal to 1, then GCD of A plus B comma A square minus AB plus B square, this is equal to 1 or 3. Similarly, second property, for any two integers, GCD of A plus B comma A power B plus B power P divided by A plus B, this is either equal to 1 or P. And similarly, we can have like this third property, GCD of n factorial plus 1 comma n plus 1 factorial plus 1, this is always equal to 1. So that means these two numbers are always relatively prime, n factorial plus 1 and n plus 1 factorial plus 1. These two numbers are always relatively prime. Okay, now let's move forward and define the Fermat numbers. Fermat numbers, there are in fact more properties of GCD and LCM that you are advised to see from some book, and in fact one book by Nevin Zuckerman, that is a nice book of number theory. Let's now define the Fermat numbers. If n belong to n, then the number of the form Fn, which is defined as 2 power n plus 1, is called a Fermat number. So now we have some properties of Fermat number for any group. So we can write like this: F1, which is equal to 2 power 1 plus 1, that is equal to 5. So this is equal to 5. Similarly, F2 is equal to 2 power 2. Or we can define the Fermat numbers from 0 also. N is greater or equal to 0. 2 power 0 plus 1. So we have this n is greater or equal to 0. N is greater than or equal to 0. Then Fn is defined in this way. So this is equal to 3. So this F0, and F1, it is equal to now 5. Similarly, F2, it is 2 power 2 plus 1, that is 2 power 4 plus 1, that is 16 plus 1 is 17, that is also prime. Similarly, F3 is prime. F3 is prime, and F4 is also prime. F4 is prime, but for F5, for 5 less or equal to n less or equal to 21, Fn is composite. And Fermat numbers also have another property, Fn and Fm, they are always relatively prime for all m not equal to n. That means any two Fermat numbers are relatively prime. Okay, now we will again move forward and we define a set which is un. So that is definition. The set un. The set, this is standard notation un. This contains the integers x such that 1 is less or equal to x, less or equal to n, and x and n are relatively prime. That means the GCD of x and n is equal to 1. So un is the set of all integers, positive integers in fact, which are less or equal to n but relatively prime to n. Now this definition of un, this gives us a nice definition which we call the Euler's totient function. So we define the Euler's totient function here. Euler's totient function, or also known as Euler's phi function. This is defined as order of un. This is denoted in this way, phi of n, which is actually defined as the order of un. So that means phi of n defines the number of integers which are less than n and relatively prime to n. Now let's take up the results as how we can compute this phi of n. So we have it in the form by theorem. So we have this phi of p power alpha. This is equal to p power alpha minus p power alpha minus 1 if p is prime. So we have a prime number p, and phi of p power alpha is p power alpha minus p power alpha plus 1 minus 1, and second phi of mn. This is equal to phi of m into phi of n, provided if m and n are relatively prime. Okay, now here we don't need to take up any formulas. These are the only two formulas for phi that are used to find or evaluate the value of any phi of n. Now first let us define the prime numbers. Prime number. We will define the prime number in the form of a result. If p is an integer, or in fact a positive integer, such that p divides ab implies p divides a or p divides b, then p is prime. This is in fact a property of prime numbers, but any number that satisfies this property will have to be a prime number. Here we will take one example to understand that composite numbers do not satisfy this property. For example, 4 divides 12. That is, 4 divides 6 into 2, but 4 does not divide 6 and 4 does not divide 2. So that means this property is not shared by the composite numbers. Now we have the Euclid's theorem, Euclid's lemma, or we can take it also as a Euclid's theorem regarding the prime numbers. Prime numbers are infinite. There are infinitely many prime numbers. There are infinitely many prime numbers. And in fact, there is a very simple and very elegant proof of this result. If we take like the list of k prime numbers, so trying to prove this result because this is a very nice proof. Suppose the number of prime numbers is finite. Suppose p1, p2, pk, this is the list of whole prime numbers. Now we will define another number n, which is equal to p1 into p2 into pk plus 1. Now there are two choices for this n. If this n is a prime number, then it will obviously be different from this list of prime numbers. So therefore we have found another prime number, so therefore the number of prime numbers is infinite. But if this number is not prime, then we have the things like this p1, p2, pk, they will not divide this n, because if they divide this n, since p1, p2, pk also divides this first term, then so pi, that next new number p, will divide 1 also. Therefore, if there is a prime number which divides these pi's, that has to be one of them, so then it also divides the first term, so then it will divide 1, so that is not a case. So therefore we will obviously find out a prime number which is different from all these pi's and divides this n. So therefore the number of prime numbers is infinite. And in fact we have a nice another property of this prime numbers, which is a theorem. If p is prime, or let's take up if n is any integer, if n is a positive integer, then summation p less than or equal to n 1 divided by p, this is always greater than log n minus 1. So now what does this result tell us is that for any integer n, if we take the sum of reciprocals of all prime numbers less or equal to n, then that sum is always greater than this log n minus 1. So this result actually tells us, so what is the conclusion? So conclusion, or this implies or implication, we can say the summation 1 divided by p is a divergent series. It's a divergent series, and that is prime numbers are infinite. There are infinitely many prime numbers. Because if we have this result and the number of prime numbers is finite, then the sum of those prime numbers will be some finite number. But since this is always greater than log n minus 1, that means we have a series whose nth partial sum is greater than some pre-assigned or fixed real number. So that such a kind of a series has to be a divergent series. So that in other words means that the number of prime numbers is infinite in number. Okay, now let's have some Fermat's theorems. Fermat's theorem. We have two parts of this Fermat's theorem. If a is an integer and p is prime, then this a power p, this is always congruent to a modulo p. And second one is a power p minus 1 is always congruent to 1 modulo p, but here we have a condition if a and p are relatively prime. So this is the Fermat's theorem. Now this Fermat's theorem has some nice applications. So let's call some applications of Fermat's theorem. It has many applications, but we will just discuss here one of them. So find the last two digits of suppose 3 power 81. So what do we do in the solution? In order to find the last two digits, we have to divide this 3 power 81 by 100. So what we are required? We are asked to find a such that 3 power 81 is congruent to a modulo 100. We have not defined congruences in this lecture, but as from the beginning, we assume that the lecture is only for those who have already completed the post-graduation in mathematics, so they know how to define these congruences. Okay. So now how do we begin? So we start like this. We know that 3 is congruent to 3 mod 100. Then we will increase the powers, and in fact we have like 3 power 4 is congruent 81 mod 100. Then this gives 3 power 5. Now multiply both sides by 3. This becomes 243 mod 100. Now divide 243 by 100. That is 3 power 5 is congruent to 43 mod 100. Now again multiply by 3. This gives 3 power 6 is congruent to 912 mod 100. Now divide 129 by 100 again. We get 3 power 6 is congruent to 29 mod 100. Now we have to keep on calculating unless we get some nice number in place of a. So now 3 power 7 is congruent to, this is 3 into 9 is 27. So this 87 mod 100. Now again multiply by 3. This 3 power 8 is 21. 3 into 8 is 24. That is 26 mod 100. Then this gives 3 power 8 is congruent to 61 mod 100. Unfortunately we have to make so many calculations here. then 3 power 9 is congruent to 3, 118 mod 100, then 3 power 10. So this is taking too much time, so I think we will erase this part here. Okay, we will take a different question that will have fewer number of calculations. Okay, we will find the last just one digit of. One digit of 3 power 81. So then in that case we have to do the calculations in mod 10. So we have to find a such that 3 power 81 is congruent to a modulo 10. Now using the calculation in a similar way, we have 3 is congruent to 3 modulo 10. Then we will have 3 square is congruent to 9 modulo 10. We can write 3 cube is congruent to 27 modulo 10, or 3 cube is congruent to 7 modulo 10, because 27 mod 10 is just 7. So that is 3 power 4 is congruent to 21 mod 10. That is 3 power 4 is congruent to 1 modulo 10. So this is what we want always here in such kinds of calculations. We want a nice number here in place of this a. Now we can immediately raise or reach closer to the power 81. This implies 3 power 4 whole power 20 is congruent to 1 power 20 modulo 10. So this implies 3 power 80 is congruent to 1 modulo 10. This implies 3 power 81, now multiplying by 3, is congruent to 3 modulo 10. So thus the last digit of 3 power 81 is 3. Thus last digit of 3 power 81 is 3. Now we will take a generalized version of this Fermat's theorem. So generalized version, which we call the Euler's theorem. Euler's theorem. So Euler's theorem states that if a and m are relatively prime, then a power pi m is congruent to 1 modulo m. 1 modulo m. But here we have the condition that a and m must be relatively prime. Now we have the similar application for this Euler's theorem. Now we can easily find last two digits of 3 power 81. They can easily be evaluated using the Fermat's Euler's theorem. So in the solution we have to find a such that 3 power 81 is congruent to a modulo 100. Since we have to find two digits, so we divide the number by 100, and dividing by 100 means the remainder will be the last two digits. So what do we have now? We have now this a. Now let's compare this m and a. So we have a is equal to 3 and m is equal to 100 in this equation. So this is equal to 1. Hence, by Euler's theorem, this 3 power pi of 100, this will be congruent to 1 modulo 100. So this implies 3 power 40. As pi 100 is 40, this is congruent to 1 modulo 100. So we have immediately reached 3 power 40 using Euler's theorem. So this implies 3 power 40 whole square is congruent to 1 modulo 100. So at this step we will have to take a power of this left hand side so that we reach close to 3 power 81. And taking power 2 we will reach 80. So this implies 3 power 80 is congruent to 1 modulo 100. Now multiply by 3. This implies 3 power 81 is congruent to 3 modulo 100. But since we have the question to find the last two digits, hence last two digits of 3 power 81 are 03. So because we have obtained, dividing this 3 power 81 by 100, we have obtained the remainder 3. So therefore the last two digits of 3 power 81 must be 03. Okay, now we shall formally discuss about the congruences. We have earlier used congruences in evaluation of this Fermat's theorem and Euler's theorem. Okay, so congruences are defined in this way. this an expression of the form, or we can define it in this way: if n is not equal to 0 and n divides a minus b, then we write a is congruent to b modulo n. Now it has the properties. The first one is this relation is reflexive, relation of congruence is reflexive, symmetric, and also transitive. Now by reflexive we know that this reflexive, what we mean by reflexive, a is congruent to a modulo n always. By symmetric we mean a is congruent to b mod n. This implies b is congruent to a mod n. That's the definition of transitivity, symmetry. And by third, for transitivity we must have a is congruent to b mod n is given, b is congruent to c mod n is given. Then these two imply a is congruent to c mod n. So that is what we mean by transitivity. So relation of congruence, a congruent to b mod n. This is reflexive, symmetric, and transitive. And we know the relation that is reflexive, symmetric, and transitive. It is called an equivalence relation. Thus, relation of congruence. Thus, relation of congruences is an equivalence relation. Now, every equivalence relation partition is the set. So, therefore, this congruences relation partitions the set of integers into disjoint equivalence classes. In fact, it always partition into disjoint equivalence classes. So now we need to write down what is the notation for those classes. If we have a is congruent to b mod n, that means if we divide the integer a by n, we will get the remainder b. So these classes are denoted by these classes for equivalence modulo n are denoted by, so this is actually the list of remainders. When integer is divided by n, we can, if n integer is divided by n, the possible remainder is 0, the possible remainder is 1, the possible remainder is 2, and the possible remainder up to the maximum is n minus 1. And or they can equivalently be denoted in this way, sometimes 0 bar, 1 bar, 2 bar, and so on, n minus 1 bar. But if the notation is understood and this set is denoted by, integers modulo n, zn, which is stated as integers modulo n. So we can write this as 0 bar, 1 bar, 2 bar, so on, n minus 1 bar. So this is how the total set of integers is partitioned. Now here the 0 represents all the integers which are multiples of n. 1 represents all the integers which are multiples of n plus 1, or which leave the remainder 1 when divided by n. And similarly 2 denotes all integers which leave the remainder 2 when divided by n. But if the notation is to be understood, we can most of the time is write simply this in this 0, 1, 2, 3 up to n minus 1. And this 0 now denotes a class, the set of all integers which are multiples of n. Okay, now let's take up one nice result regarding this equivalences. So this is a kind of a theorem. If f of x is a polynomial function, and a is congruent to b modulo n, then f of a is also congruent to f of b modulo n. So therefore the equivalence. Therefore, this congruence relation is preserved by a polynomial function also. Okay, now let's have some more properties. Okay, now let's write down the properties like this that need to be remembered. If this is a kind of a theorem, if P is prime and P is congruent to 1 modulo 4. So these are the special kinds of prime numbers. Then there exist integers a and b such that p is equal to a square plus b square. So this theorem tells us that every prime number that is congruent to 1 mod 4 is always a sum of two squares. This has a very nice application when to study the ring theory of ring of Gaussian integers modulo n. Now let's take up the algebraic congruences. So now solutions of congruences. So consider linear congruence of the form, linear congruences. Linear congruence Ax congruent to b modulo n. Now how do we find its solution? Before finding its solution, we will come back to the division algorithm. So using division algorithm, find GCD of, okay, let's find the GCD of anyway, let's take up 10, 46. Okay. So what do we do in the solution? So we here remember one property of the division algorithm. If A is equal to PQ plus R, then GCD of A comma B is same as GCD of B comma R. So GCD of these two numbers, GCD of A and B, it is same as GCD of B comma R. So that is the property of the division algorithm that we will use to find out the GCD of 10 and 46. So here we will write this 46 as 10. We will divide this 46 by 10. The quotient will be 4 and the remainder will be 6. So now we have 10 as our B and R as our remainder, 6 as our remainder. So now we will divide this 10 by 6. So 10 is equal to 6 into 1 plus 4. So now our divisor is 6 and remainder is 4. Now we divide the 6 by 4 into 1 plus 2. Then finally we divide this 4 by 2. We get 2 into 2 plus 0. So therefore this last non-zero remainder, is defined as the GCD of the two numbers A and B. So this implies GCD of 10, 46, that is equal to 2. Now we can also use the Bezout's identity. Now Bezout's identity speaks as that. So now our next question is find x and y such that 10x plus 46y is equal to 2. So now let's see what is this x and y. We can reverse from this step here. We will write this 2 is equal to 6 minus 4 into 1. But from the previous step we have the value for 4. So we can write this 2 is equal to 6 minus. Now instead of 4 we write 10 minus 6 into 1. Now multiply this by 1. So this is equal to 6 minus 10 into 1, then plus 6 into 1. So this is equal to, now 6 into 1, that becomes 6 into 2 minus 10 into 1. But now in the previous step we have the value for the 6 also. Now 6 is equal to 46 minus 10 into 4. Now multiply this 2 minus 10 into 2. So this is equal to 46 into 2 minus 10 into 8 minus 10 into 2. So this is equal to 46 into 2 minus 10 into 8. We can take 10 common, so it is minus 10 into 10, which can be expressed as 46. Now we can write 2 in the bracket plus 10 and write the next minus 10 in the bracket. So therefore, this 46, this is our A, this 10 is our B, this 2 is our X, and this minus 10, that is our Y. So therefore, X is equal to 2. Now since we have written 10X, so X is our minus 10, so we can write it in that way. So this is our Y actually, and this one is our X. And in fact also we have taken this to be A, we have taken this one to be A and this one to be B. So that means we have, using the division algorithm also, we have found the values of X and Y also. Now let's come back to the linear congruences. So solve the congruence. So first we will have a theorem like this. The congruence AX congruent to B mod n has a solution if and only if GCD of A comma n, which we call as D, it must divide B. And in this case the congruence has D solutions in Zn. We can call D solutions modulo n also. And we also take a generalized version of this result. So another generalized version is generalized version of the same result. If we have a linear congruence in n variables, if a1x, or we can say the congruence a1x1 plus a2x2 plus so on plus anxn congruent to B modulo n has a solution if and only if GCD of a1 comma a2 comma an comma n, which we call as D, this now must divide B. And in this case the number of solutions is the number of incongruent solutions is D this is equal to dm power n minus 1. So there is a formula for calculating the number of incongruent solutions, or we can say the solutions in the number of solutions in Zn. Now our exercise. Now let's solve this exercise. Or before doing this exercise, we will have one more property of the congruences. If, or we can say it property like this, if like this Ka is congruent to Kb modulo n, then A is congruent to B modulo n divided by GCD of n comma k. Okay, so that's our one property here. Another property is if x naught is a solution of Kax, or we can write it like this, is a solution of this is a solution of Ax congruent to B modulo n divided by GCD of nk, then, or write it like this, GCD of, if this has a solution x naught, then x naught is also a solution of Kax is congruent to Kb modulo nk. So we can multiply any number k here, then the solution of this basic congruence will also be a solution of this new congruence, so obtain it. Okay, now we are ready to solve one exercise. So find all solutions of, moreover, we mentioned one more property here. That's a very nice property, and in fact it will help us a lot in finding all the solutions. If x naught is a solution of ax congruent to b mod n, and let GCD of a comma n is equal to d, then the other solutions are x plus n by d. So that's what it tells us, that that is the solution is of ax congruent to b modulo n, theorem and arithmetic progression, with common difference n by d, where d is the GCD of a comma n, and we know the solution exists for this congruence if this d divides b. Okay, now let's come to the exercise. Find all solutions of this 15x is congruent to 25 modulo 35. We will use all these above properties of congruences to solve this exercise. So we are given 15x is congruent to 25 modulo 35. First of all, the GCD of 15 and 35 is equal to 5, and 5 divides 25. So thus this congruence has a solution. Thus the congruence has now GCD is equal to 5, solution has 5 solutions in Z35. So therefore there are 5 solutions in Z35. But always, in order to make our question easier, we will divide the common factor of 15, 25 and 35 throughout the congruence. So 15x congruent to 25 mod 35. This gives another congruence, divide throughout by 5. This gives 3x is congruent to 5 modulo 7. Now this congruence is a little bit easier to handle. Now here in this congruence, again 7 and 3 has GCD 1, and 1 divides 5. So this will have a unique solution in Z7. So now let's find out the solution by hit and try also. In fact, we have the Z7 as 0, 1, 2, 3, 4, 5, 6. Now let's try out these numbers. Now as 0 is not a solution, 1 is not a solution, 2 is not a solution, 3 is not a solution, 4. 12 minus 5, or in fact 4 is a solution. So clearly 3 into 4 is congruent to 5 modulo 7. Because 3 into 4 is 12, 12 minus 5 is 7, and 7 divided 7. So therefore 4 is a solution. But now, as using the previous property, hence x equal to 4 is a solution of given congruence. 15x is congruent to 25 modulo 35. In fact, this will be the sum of all the solutions among Z35 for this congruence. Now, as we know, the other solution is all the set of all solutions form an arithmetic progression with common difference n by d. So now n by d here, as n is equal to 35 and common this d, which is the GCD of that is equal to 5, so n by d is equal to 7. Hence the solutions are so first solution we have 4, the next will be 4 plus 7, that is equal to 11, next will be 11 plus 7, that is equal to 18, next will be 18 plus 7, that is equal to 25, and another solution is 25 plus 7, that is equal to 32. Now 32 plus 7 will be bigger than 35. Now let's count if these are exactly 5 solutions. So this is 1, 2, 3, 4, 5. These are the 5 solutions of the given congruence in Z35. So we have done the solution also for a linear congruence. Similarly, we can solve the other linear congruences. Okay, now let's come to have some more properties. So these are some more results, theorems, which are necessary for the examination. If a power p is congruent to a modulo p, a mod p, and a power q is congruent to a modulo q, then a power pq, this is also congruent to a modulo pq. So let's remember this result. Another one is the congruence x square is congruent to minus 1 mod p has a solution if and only if either p is equal to 2 or p is congruent to 1 modulo 4. So therefore the only possibility that this congruence has a solution is either p must be 2 or p must be congruent to 1 modulo 4. Now the question is regarding this result here can be asked like, which of the following congruence has a solution? Which of the following congruences has a solution? The congruences will be given in this way, like suppose x square is congruent to minus 1 modulo 17. Suppose second one is x square is congruent to minus 1 modulo 31. The third one is x square is congruent to minus 1 modulo 47. The fourth one is x square is congruent to minus 1 modulo 41. Now we have to check quickly in the examination within half a minute or a minute that which of these following congruence has a solution. We just have to compare this with x square congruent to minus 1 mod p. Now it has a solution if p is either 2 or p is congruent to minus 1 mod 4. Now we know that p is equal to 17, 31, 47 and 41. So 2 is not a case. And the second case is we need to check that if 4 divides p minus 1. So if 4 divides p minus 1. Now 17 minus 1 is 16. So 4 divided 16, it has a solution. 47 minus 1 is 46. This does not have a solution. 31 minus 1 is 30. It is not satisfied. It does not have a solution. 41 minus 1, that is 40. So this also has a solution. This is how the questions can be asked regarding this kind of an exercise. Now let's have some more definitions. Or we can say the notations. This is the notation. The earlier notations that we have defined is pi n. Now we define the notation tau n and we define the notation sigma n. Now this tau n is defined in this way. This is equal to alpha 1 plus 1 into alpha 2 plus 1, so on, alpha k plus 1. This is actually number of divisors of n equal to p1 power alpha 1, p2 power alpha 2, so on, pk power alpha k. So if we have an integer n that has this canonical form, then the number of divisors is given by this formula and the sum of divisors is given in this way. This is equal to p1 power alpha 1 plus 1, then minus 1 whole divided by p1 minus 1. Now multiply it by p2 power alpha 2 plus 1, then minus 1 divided by p2 minus 1, then product pk power alpha k plus 1 minus 1 divided by pk minus 1. So this second formula, this is equal to sum of divisors of n, which is having the canonical form p1 power alpha 1, p2 power alpha 2, so on, pk power alpha k. Now let's also mention some more results here that may be asked in the examination. This is tau n is odd if and only if n is a perfect square. And similarly, sigma n is odd if and only if n or 2n is a perfect square. So these are the two results regarding these two functions, sigma n and tau n. Now let's have some more properties. This summation k belonging to un, k, this is equal to n pi n divided by 2. Now what does this result tell us? This is actually sum of all integers, all positive integers less than n and prime to n. So sum of all integers which are less than n and relatively prime to n, their sum is given by n pi n by 2. And we have another property, the product of all divisors of n. Product d divides n d. So this is equal to n power tau n divided by 2. So this is equal to product of all positive divisors of n. So these are also two nice formulas. So let's have an example on both of them. So apply these above formulas. So if suppose n is equal to let's take one simple exercise. N is equal to, okay, let's take up n is equal to 10. So then divisors are 1, 2, 5, 10, and also u10, this is equal to 1, 3, 7, 9. So then 1 plus 3 plus 7 plus 9, that is equal to 20. And now let's compute it using this above formula. Now what is this? N phi n by 2. This is equal to 10 into phi of 10 divided by 2. That is 10 into 4 divided by 2. This is equal to 20. So therefore the sum of integers in u10, that is 20, which is obtained in this way. And similar the product of divisors. Second, next, product of divisors 1 into 2 into 5 into 10, that is equal to 100, and n power tau n divided by 2. Now n is equal to 10. Tau n is the number of divisors. Number of divisors is 4 divided by 2. So that is equal to 10 square, which is equal to 100. So both of these formulas are verified in this way. Now let's do the final important topic of this lecture, which is the Chinese remainder theorem. Or before doing the Chinese remainder theorem, we will try to learn how do we find the inverses. Anyway, we can do the inverse using the Chinese remainder theorem as well. So Chinese remainder theorem. Chinese remainder theorem. This states that given the congruences x congruent to a1 modulo m1, second x congruent to a2 mod m2, then so on, x congruent to ak mod mk, where mi, mj are relatively prime for all I not equal to j. So we have the congruences, but the moduli should be relatively prime. Then these congruences have a common solution, given by, which we denote by x, which is equal to a1 m1 into m1 inverse mod small m1, then plus a2 m2 inverse mod m2, then plus so on, plus a k mk, then mk inverse mod mk. Now then finally we have to calculate this whole modulus as modulus of m. Now we have defined these capital MIs and capital M, where this capital M, this is equal to m1 into m2 into mk, and these capital MIs, this is equal to m divided by mi. 1 less or equal to I less or equal to k. So this is how do we define. Now first let's understand this properly. We are given first k congruences, and m1, m2, mk, they must be pairwise relatively prime. Then the common solution of these k congruences is given in this way: a1 into m1 inverse modulo m1. So now here we have an important step. This m1 inverse has to be calculated in modulo m1. m2 inverse has to be calculated in modulo m2. So therefore this m1 inverse into this m1, this will not be equal to 1, because this m1 is general m divided by m1, but this m1 inverse has to be calculated only in mod m1. m2 inverse in only mod m2, and the whole modulus is divided in as modulo m, while m is the product of all moduli. Now let's take up an exercise. So find the solution of, we will take a common solution of the congruences: x congruent to 5 modulo 7, x congruent to 7 modulo 11, then x congruent to 3 modulo 13. We have to find the common solution of these three congruences, and within the solution we will also learn how do we find the inverses of the elements, and we will also discuss which elements have the inverse. So let's begin with the solution. So here we have a1 is equal to 5, a2 is equal to 7, a3 is equal to 3. m1, the first modular, is 7, m2 second modular is 11, m3 the third modular, that is equal to 13. So hence capital M, which is now defined as m1 into m2 into m3, which is 7 into 11 into 13. Now multiplying these we get 1001. Now capital M1, that is equal to this 1001 divided by 11. So this 1001 divided by m1, so this will be actually equal to 7 into 11 into 13 divided by 11, sorry 7. So this is equal to 11 into 13, and this 11 into 13, this is equal to 143. Similarly, we calculate m2 as 91 and m3 as 77. So m2 is equal to 7 into 13 and m3 is 7 into 11. So therefore we can write down the solution. Therefore the solution x, that is equal to a1 m1, now m1 inverse modulo m1, that is modulo 143, sorry, that is modulo small m1, that is modulo 7, then plus a2 m2, now m2 inverse modulo, we shall write, instead of this we will write m1 here, now modulo m2 here, then plus a3 m3 inverse modulo small m3, and then whole modulo has to be computed in m. So now let's substitute the values. Now a1, that is equal to 5 into a1 is 5, m1 is equal to 143. Now m1 inverse modulo small m1, that is 7, then plus a2 is 7 into m2 is 91, and then m2 inverse modulo m2, that's 11, then third one is 3 into 77, then m3 inverse modulo the third modulo, that is 13, and whole modulo has to be computed in 1001. Now this 5 into 143, okay, now first let's calculate this m1 inverse mod 7. So now m1 inverse. How do we calculate m1 inverse? So for this, we have to solve the congruence m1x congruent to 1 modulo 7. Actually, inverse means we have to multiply this m1 with a number with the product is 1 modulo 7. So this gives, now what's value of m1? Now m1 is equal to 143. So 143 into x congruent to 1 modulo 7. Now how do we solve this congruence easily? First we will divide this 143 by 7. So this gives us, now 143 divided by 7 just leaves the remainder 3 because 7 into 20 is 140. So this becomes 3x is congruent to 1 modulo 7. Now in Z7 we have to check up the numbers, which of the numbers satisfy this. So then x is clearly equal to 5 because 3 into 5 is 15 and 15 minus 1 is 14. 14 is a multiple of 7. So m1 inverse is therefore 5. So that is m1 inverse, that is equal to 5. Now for m2 inverse, we again have to solve a similar congruence. m2x is congruent to now 1 modulo small m2, that's 11. So now substituting the value of m2, m2 is equal to 91. So this is 91 x congruent to 1 modulo 11. Now dividing this 91 by 11, this gives 3x is congruent to 1 modulo 11. Now checking in Z11, so this gives x is equal to now 4 because 3 into 4 is 12, 12 minus 1 is 11, that is this m2 inverse, this is equal to 4. So we have obtained the value of m2. Now similarly for the practice purpose, m3 inverse, for m3 inverse we have m3x is congruent to modulo 13, that is now m3, that is 77 into x is congruent to 1 modulo 13. Now dividing this 77 by 13, 13 into, okay, 13 into 7 is somewhere 69, and this gives 8x, or 8x is congruent to 1 modulo 13. Okay, 13 into 5 is 65, so this is false. Into 5 is 65, so this becomes 12x is congruent to 1 modulo 13. So this implies now 12 into 12 is which can also be written as, or we can, instead of 12 we can write minus 1x is congruent to 1 modulo 13, or x is congruent to 1 modulo 13, or x is congruent to, now minus 1 is congruent to 12 modulo 13. So what we have done here, so at this stage we have used 12 is congruent to minus 1 mod 13. So instead of 12 we write minus 1. Now we shift this minus 1 onto the right hand side, and now here minus 1 is congruent to 12 mod 13. So therefore x equal to 12, that is m3 inverse, this is equal to 12. Or we can even use minus 1 in our calculation. So hence our solution is x equal to, this is 5 into 43, 5 into 143 into m1 inverse, that was 5, then plus 7 into 91, 7 into 91 into m2 inverse, that was 4, then plus 3 into 77, 3 into 77 into 12. Now we have to calculate this whole as in modulo 1001. So now let me add up all these numbers. 5 into 143 into 5. Okay, then plus 7 into 91 into 4 plus 377. So it is 8895 modulo 1001. 8895. So this becomes 887. This is 887 modulo 1001. So this is 887 is the common solution to all the given three congruences. Thank you very much. In the next lecture, we will study some advanced topics of number theory, like the second part of the syllabus that is asked, like the Mobius functions or the primitive roots,